Good morning, friends. Now we are discussing continuity equation in module number 2, fluid kinematics of the subject fluid mechanics. So we have now derivation of a continuity equation for study three-dimensional incompressible flow. To derive the continuity equation, we are taking a fluid element of length dx, dy and dz in the three axes x, y and z directions. Let u, v and w are the velocity components in x, y and z directions respectively. So along x-axis we have the length dx and the velocity component is u. Along y-axis the length is dy and the velocity component is v, and the vertical axis, that is z-axis, the length is dz and the velocity component is w. So x, y, z directions we have the lengths dx, dy and dz, and the velocity components are u, v and w respectively. So we know mass flow rate is equal to density into area into velocity. So mass flow rate is density into area into velocity. So here rho is the density of the fluid, uh, u is the velocity component in x direction, and dy dz. So we have the phase ABCD. So the fluid is entering on the left side ABCD in the fluid element. So the area of the face ABCD is now having dy is the length along y-axis and dz is the length along z-axis. So the area of the face ABCD is dy dz. So mass uh, living now, right? So that is the mass of the fluid entering the phase ABCD is rho into area of the phase ABCD into velocity in x direction. So rho into, so velocity in x direction is u and area of the phase ABCD is dy dz. Now mass of the fluid leaving the phase EFGH, that is on the right hand side. So the fluid is traveling for a distance dx in x direction and leaving the phase, that is fluid element in the phase EFGH. So that mass leaving is now the original mass, that is rho into dy dz plus the rate of change of the mass, that is del by del x of this original mass, that is rho u dy dz, and the fluid is traveling for a distance dx, that is the fluid when it travels for a small length dx, so I have some change in the mass. Either the mass will be getting accumulated or deducted. So if there is accumulation of mass, it is plus. If there is deduction of mass, so that is minus. So if I move 1 unit of distance in x direction, how much mass flow is increased or decreased? So if the gradient is positive, so that is the gradient is nothing but del by del x of rho u dx dy dz. The fluid is accelerating or expanding as it is moving to the right. If the gradient is 0, that means the flow is perfectly steady. Whatever mass enters the fluid element, the same amount of mass it is leaving. If this gradient is negative, the flow is slowing down or getting compressed. So the gradient del by del x is telling you if the fluid is speeding up or slowing down as it is crossing the fluid element. So dx, dy, dz, the product of these three dimensions is telling how much the big the room is. So gain of mass in x direction. So that is mass entering in the left hand side, that is ABCD, and mass leaving the face EFGH. So the difference of these two. So that is mass of the fluid entering the phase ABCD minus mass of fluid leaving the phase EFGH. So I have now net gain of masses. So that is del by del x of rho u plus del by del y of rho v plus del by del z of rho w. So in all the three terms I have dx, dy, dz common. So that is taken outside. Since the mass is neither created nor destroyed, that means we have net gain of masses is equal to rate of increase in the fluid mass. That is, the mass is entering the phase on the left hand side ABCD and it travels for a distance dx. So it travels for a distance dx and leaving the phase EFGH. So I have uh, the rate of increase of the fluid mass with respect to time. So there is increase in the fluid mass. So that is del by del t of rho of dx, dy, dz. So the net gain of masses is equal to the rate of increase of the fluid mass. That is the rate of increase of the fluid mass with respect to the time t. So now we know that the mass is neither created nor destroyed. So we are taking the summation. So that is taking the entire negative components on the other side so that it becomes positive on the left hand side, 0 remains. So I have del by del t of rho plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w is 0. So dx, dy, dz get cancelled on both the sides. So for steady flow, I have there is no change in the density with respect to time. So del rho by del t is 0. So the first quantity in the equation becomes 0. So now I have only 3 terms in the equation. Earlier we have 4 terms in the equation. Now for steady flow, del rho by del t is taken as 0. So we have only 3 terms in the equation. For incompressible flow, that means the fluid cannot be compressed, means my rho, that is density, is constant. So rho is taken outside from all the 3 quantities. Now we left out with only del u by del x plus del v by del y plus del w by del z is equal to 0. This is continuity equation in 3-dimensional flow. Thank you, friends.